Yeah, swear to go.
It's an Aces. Yeah, I don't even know, honestly. It's freaking good.
Check.
It gets hot. Iris? Zephyrus? Yeah. I knew all about it when I bought it.
I almost got a gaming laptop because I needed a new laptop this year, but I needed to be able to write on the screen just in case. So I got this one. It's okay. I mean, it'll work. Hello, hello.
Yes, and I regretted it afterwards because my battery got messed up like that. I was like, those things, if I would have closed again, we're taking battery. I had to take it to the shop. It's like soldered in there.
Can y'all hear me at home? See my screen?
Yes.
Yes, everything good? Okay.
Right. Nothing replaceable.
This weekend, I decided my desktop computer at home has a 500 gig hard drive on it. And I have like 5 other drives on the computer, you know, and they're all like at least a terabyte.
Yeah.
And so I was like, I want my hard drive to have more space because it's only 500 gig and I'm about 60% full. So I'm like, I'm going to put a 2 gig SD or solid state, right? SSD. And man, what a fiasco. Like it was easy. Like I cloned it, everything. And then I, you know, increased the partition. So everything was good. But when I tried to boot, it wouldn't boot. And then I went in and messed with the BIOS and I freaking jacked it up. And it took me 8 hours to get that thing fixed. But I finally got, I basically had to start over with Windows again. So, but that's at my home desktop. So, but I'm good now. It's you know, it's clean. There's nothing on it, but my programs and my data. Took forever, but I have, what, 2 terabytes now. All right, everyone. Glad y'all are here. I'm glad I'm here. This is Thanksgiving week. So, you know, Wednesday, I'm technically not allowed to cancel class. So I will be here. If you're not here, if you have to travel or something, you know, I understand. If I have to stand here by myself, I will. But I will be on campus on Wednesday. All right. We will have class. All right. So last class, we were talking about 8.5, right? That's what we did, 8.5. And just talking to some of your classmates in here, I know not everyone has gotten through the homework on this, but that's what Thanksgiving is for, right? To sit and do homework. So we talked about PowerSeries last time. We talked about basically how every function can pretty much be turned into a PowerSeries, but we have to be careful because it will have this thing called an interval of convergence, meaning that that function that we can convert to a PowerSeries is only valid. That conversion to a PowerSeries is only valid within this certain window. And for some functions, it's only valid at a single point, which is useless. And then other functions, it's valid on an interval, which is helpful. And then when the best case is when it's valid on the entire number line, which means that there's always a way to convert that function into a PowerSeries. That's what we learned about, okay? And gave you a couple of examples where you went and found the interval or radius of convergence and interval of convergence. The next section is about how do we turn a function into its PowerSeries, okay? So instead of starting with the PowerSeries and saying, hey, look at this PowerSeries, let's see what its interval of convergence is, let's look at a traditional function and see how to change it into its PowerSeries. Make sense what we're trying to do? Now, to start, let me try and give you a preview. In this section, what we're going to do is we're going to look at a specific function that we know its PowerSeries already. We're going to look at one specific function where we know its PowerSeries, and we're going to use that to be able to represent some other functions as their PowerSeries. In 8.7, we get we get the final method to take any function and convert it to its power series. So 8.7 is the huge sections where we study what are called Maclaurin and Taylor series. And that's basically the method to convert a function into its power series generally. This section, we're still very isolated into one particular type of function. So where we are, now that we know what a power series is and how to determine the radius of convergence and interval of convergence, we attempt to take some known functions and see how to rewrite them as power series. Did I send you all these notes already? The 8.6? Yes, I'm seeing nods, yes. Okay, they should be, let me just check. I thought I sent them last week, but I could maybe not have. No, I didn't send you all 8.6. Okay, I'll send these to you after class. I apologize. So everything you see here will be provided to you later. All right, so we're going to start with some known function and convert it into its power series. So something familiar. We have already seen last class that if you take this power series, sum n equals 0 to infinity of x to the n, that can be rewritten, as its series 1 plus x squared, that is basically a geometric series, and that it will converge so long as the absolute value of x is less than 1. So that is the known series that we're going to work with today, that one and that alone. And from that, we're going to build all these other functions power series from that. Okay? So we now show how we can use this power series to determine the power series for functions which are similar to this one. So let's take a look at this first example. Oh, I'm leaving something out. What does this converge to? Why didn't I put that in there? What does this converge to? If I left this out of the notes, this is very important. So this is a geometric series, right? And it will converge if the absolute value of x is less than 1. And what does it converge to? What was the formula for a geometric series? What does it converge to? No. There's
A
a
over
formula.
1 minus r.
What is that?
A over 1
A over
minus
1
r.
minus r. A over 1 minus r is what it converges to. Look, I'm going to have to bring up the notes from last class. 8.5. The first example. Yeah. No. Oh, here it is. A first and important example. This one right here. This is what we did last class. And we say that this will converge to, right here, this is from last class. This converges to 1 over 1 minus x. All right, that series will converge to 1 over 1 minus x, so long as the absolute value of x is less than 1. And we need that for today. So that's what I forgot to put in here. This series will converge to 1 over 1 minus x. In other words, this function, 1 over 1 minus x, this function right here is equivalent to 1 plus x squared plus x cubed plus x to the 4th plus ... forever if the absolute value of x is less than 1. If you were to graph these two things, you get the exact same picture as long as the absolute value of x is less than 1. And I showed that to y'all last class. I showed it to you. Here it was. Here's the red is the 1 over 1 minus x. The black is the power series. And I showed you how if I start adding more terms to this power series, that the black converges to the red one within that little window between -1 and 1. Right? That they basically become the same functions. All right, now how are we going to use this to find the power series for some other unrelated functions? Or not unrelated, they're different functions. They are related, actually. So let's do this. First example. Let's find a power series and then find the interval of convergence for this. I need to open up one more program. I think I might go maskless today. Okay, we're going to do this example. All right, now, first of all, do you agree that that function right there, 1 over 1 plus x squared, that is definitely not the original, that's not the one we were just looking at, 1 over 1 minus x. But we're going to still try and find its power series. So here's what I want you to realize. This is really the same as, now remember, I'm going to put it over here to the side. We have a formula for 1 over 1 minus x. That is equal to 1 plus x squared plus x cubed plus dot, 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 right? We know that. Now, on this formula, another way I could write it is 1 over 1 minus u equals 1 plus u. Oops, up there I put x squared first. X plus x squared dot, dot, dot. So down here, this should be 1 plus u squared plus dot, dot, dot. Right, so if I replace the x with u, I've got the same thing, right? Okay, so over here on this, we're just going to rewrite it. I'm going to write it as 1 over 1 minus negative x squared. That's the same thing, right? Subtracting a negative. Yeah? Now, this in here in the parentheses, that's u. That's like my u in that formula. So now it looks like 1 over 1 minus u, right? This will turn into 1 plus what? U, right? Plus u squared plus u cubed. But what's u for us? Negative x squared. So this is going to be 1 plus negative x squared plus negative x squared squared plus negative x squared cubed plus negative x squared to the 4th plus dot, dot, dot. Do you understand what I'm doing? It's just a substitution. I'm taking this negative x squared, I'm replacing it with u, and then I'm using the formula here. That seemed pretty simple. It's just a substitution. Now I'm going to clean this up. This is equal to 1 minus x squared plus x to the 4th minus x to the what? You'll see what I'm doing here? 6th, x to the 6th. Right? Last one here that I'm going to put plus, right? X to the 8th. Anytime I had an even power, right? When you look at these powers here, when I had an even power, when you square this, it becomes positive. And when you raise this to the 4th power, it's positive. But then when you raise these to odd powers, it stays negative, right? So that's it, right? According to the formula. Now, but that, can we rewrite that in sigma notation? Is there any way you think you could come up with this sigma notation for this? Start at n equals 0, and then like this. So it's an alternating series, right? It's an alternating series. It starts out positive, so I'm going to go -1 to the n. Notice we're starting at 0 here, right? So I'm going to have to go -1 to the n. That way, the first time when I plug in 0, I get -1 to the 0, which is positive. What about the x's? All of these x's have powers. What are the powers on these x's? Evens, right? We know how to create the list of even numbers. And the first one, even though it's not written, this is like an x to the 0, isn't it, right there? So I should put here x to what power? How do we get evens starting at, we need to start at 0 though, right? So 2n? 2n? That should do it, right? Okay, that is the power series for that function. If we were to graph this function and then start graphing this power series, they should start looking really close to one another. Does this make sense? But where will they start looking like each other? Everywhere? What's the interval of convergence? Well, what was the condition? What was the condition over here on these on the side? What was the condition we had in order for that to be true? We had to have the absolute value of x less than 1, right? And for us, the u is our thing that needs to have an absolute value less than 1. So this is true, right? All of this is true only if the thing that we plugged in for u, negative x squared, that absolute value is less than 1, right? This is all true only if that's true, right? Now, since it's an absolute value, I can get rid of the negative there. And then how do we solve this? We can drop the absolute value if we put a negative 1 on the other side. That would be our interval. That would, well, we need to get rid of the squared, right? We have to get rid of the squared. So what are your restrictions here? Isn't this the same? Wouldn't this be the same? Think about it this way. If I take a number and square it and need it to be between negative 1 and 1, then I just need to take any number between negative 1 and 1. Because if I take any number between negative 1 and 1 and I square it, I'll still land between negative 1 and 1. All right. Let me do something a little different. So what I did here is I took this, I made it look like one of these, right? That's what I did. And then once I made it look like this, I rewrote it using this formula. I'm going to do it slightly different, but we're going to get the same answer. So what I'm going to do is I'm going to take this, and instead of actually writing it out term by term like I did, I'm just going to turn it into what the formula says it's supposed to be. So this is supposed to be sum n equals 0 to infinity. Let's go back to the notes, right? This 1 over 1 minus x is equal to this. That's what we did the first time we went through this. Now we're going to instead just write it directly into that formula. Okay. But for us, instead of using x, right? Instead of using x, what are we going to use? The u, but the u is the negative x squared, right? So it's going to be something like this. Well, you tell me. What's the u? Or yeah, what's the u here for us? Negative x squared. So in the formula, whatever that x is, or we're calling that the u, whatever that is, in the formula is just the sum n equals 0 to infinity of whatever that is to the nth power, right? So I'm going to write here in parentheses negative x squared and then raise that to the nth power. Now, are these two formulas the same? Are they the same? They are. Now, I'm going to show you they're the same by doing this. I'm going to rewrite this as negative 1 times x squared to the n. That's what that really is, right? Negative 1 times x squared to the n. And then I'm going to apply the n to each of the factors. So this would be sum n equals 0 to infinity of negative 1 to the n, and then x squared to the n. And what happens when you do x squared to the, x squared to the n? You can multiply these, right? And you get x to the 2n, and that'll take you right up to this formula. You get the same exact thing. That make sense? So there's kind of like, what's that saying? 2 ways to skin a cat. Have you heard that before? I don't know where that comes from, but so one way to do this was to say, okay, let me rewrite this as this, and then just write out the terms, and then clean it up, and then find a formula. That was one way. The other way would be just go directly to the summation. Once you're here, does everyone see that once you're here, you can create this list very easily? Because once you're here, you just start plugging in values of n, and you will generate this right off the bat. So which way should you do it? Totally up to you, but you should be comfortable both ways. You should be able to write out the list and then create the formula, or create the formula or the summation and then write out the list. Both ways. They have their advantages and disadvantages, like doing one before the other. Or let's try a different one. Oh, why isn't that open up? All right. I'm going to put this down here. Okay, I'm going to reiterate up on top again that if we see 1 over 1 minus u, this can be rewritten as 1 plus u squared plus u cubed plus ... which is the same as the sigma notation, sum n equals 0 to infinity of u to the n. This is all true if the absolute value of u is less than 1. That's kind of our master formula here. All right. Now for us, we're trying to find this power series for x to the 4th over x plus 5. Right now, this doesn't look anything like what we have in our formula, right? Like in our formula, we have a 1 on top, and then it's 1 minus u. So just, you're here to learn. Watch what I do here, okay? I'm going to take this and start rewriting it. First thing I'm going to do is write it as x to the 4th times 1 over. I'm going to write it this way, 5 plus x. So all I did was I took the numerator, x to the 4th, slid it off to the side, which is the same thing, right? It's multiplication, so I can do that. And then I rewrote the 1 over the denominator. I switched the position of the 5 and the x. Now what I'm going to do is I'm going to try and create the 1, right? This formula has a 1 here. We have a 5 here, right? There's a 1 there. There's a 5 here. I don't want that 5 there. I'm going to factor a 5 out of the denominator. So this is the same as x to the 4th plus 1/5 times 1 over 1 plus 1/5 x. So that's a little tricky because what you're doing is you're pulling a 5 out, right? You're factoring a 5 out of both of these. When you factor a 5 out here, you get a 1. There is no 5 to factor out here, so you have to create a 1/5 in front of it. And the 5 that I pulled out the bottom, I represented as a 1/5 out front. Does that all make sense? Yeah, that's just algebra there. Okay, this is equal to, y'all okay at home? Any questions?
I'm good.
Okay, so now what I did was I changed that plus that was here. In the formula, I need a minus, right? So I made it a minus minus. Do y'all see it? I've created it right here. This is it. That looks a lot like 1 over 1 minus u. What would the u be here for us? Negative 1/5 x. Good. Okay, so what do we know? We know that 1 over 1 minus u can be rewritten. I can do it term by term. I can start writing it out term by term, or I can go straight to the formula, right? This time, I'm going to go straight to the formula, right? I'm going to go straight to the formula this time. So I'm going to rewrite this as x to the 4th times 1/5 times, now everything in red there, I'm going to write it in red so you can tell where, that this matches up with what's in there. Sum n equals 0 to infinity of what? What does the formula say? That all this will be equal to sum n equals 0 to infinity of u to the n, right? And u for us, we just said was negative 1/5 x all to the nth power, right? All right. We have an important little detail to notice here. This summation, right? This summation, the index has as the variable n, right? N is our index variable. So as I change n, right, it changes the power on x. But this index has no impact on x itself, right? Like we're not changing x as we start changing the values of n. X is always stuck, which means that we can take anything out here and push it into the sum, okay? Because this is just multiplication. This is not impacted by n, right? So what I'm going to do next is move the stuff that's outside inside. And when I say move it in, I'm just going to multiply it. So it's going to become sum n equals 0 to infinity. Here comes the x to the fourth inside, and then 1/5 comes inside. And then I still have the negative 1/5 x to the n. Now, if you're having trouble understanding why that's allowed, think of it this way. This whole expression is really just x to the fourth times 1/5 times, and then the summation is just a bunch of things being added together, right? Maybe there's some subtractions in here, but do you all agree it's just a bunch of terms that go forever? And so if you have something out front, you could distribute that to each term, which would be the same as just putting it in front of each term here in the sum. It has the same effect. So that's why it's allowed. I hope that makes sense. Now, this is a power series, but it is not written the way we like to write it. We like to get like just the x to a power and everything else separated. That will be very useful to us later, all right, today and next classes. So what I'm going to do now is I'm going to write sum n equals 0 to infinity. I'm going to write x to the fourth times 1/5. Now watch what I do here, okay? Watch this. I'm going to do negative 1 to the n, 1/5 to the n, x to the n. So I essentially took this negative 1/5 x to the n, and I kind of thought of it instead of that. I thought of it as a negative 1 times 1/5 times x, right? Three things multiplied together here, each one of them raised to the nth power. The reason I did that is because I want to put these two together. See, I had a 1/5 here. Now I have a 1/5 and a 1/5. I can put those together. That should be 1/5 to what power? What do you do here? I have 1/5. This is like a 1/5 to the 1, right? So you add the exponents. So n plus 1. Sum n equals 0 to infinity. Let me do that negative 1 to the n out in front. Then I have a 1/5 to the n plus 1 power. And then watch this. X to what power? N plus 4. N plus 4. X to the n plus 4. That I got by putting those two together, adding the exponents. This is our power series. That's a nice version of our power series right there. Now, if I wanted to do the terms, let's do the terms. Let's actually write out a few of these. Of course, there's an infinite number of them, right? But I'm just going to start writing out a few of them. So if I replace n with 0, I get a positive, right? N with 0 here, I get 1/5. And then x to what power? X to the, we start at 0, careful. X to the fourth, okay. Now my next term will be negative, right? And then I'll have 1/5, but this time to the, what, we're plugging in 1, so 1/5 squared, right? So we're gonna have 1/25, x to the 5th power. Got it? And then plus 1 over 125, x to the 6th, minus 1 over another 5 times that. What's that? 625? Why is my brain not working? Yeah, 625, I think. X to the 7th plus ... And that keeps going. Now, all of this is true. Be careful here. All of this is true, right? Everything we see here is true if what though? Remember, we have talked about that interval of convergence. Okay, so we said that this original top one is true whenever the absolute value of u is less than 1, right? What was u for us? It was negative 1/5 x. So this is all true if the absolute value of negative 1/5 x is less than 1. I can get rid of the absolute value on the, or I can get rid of the negative on the 1/5. This has to be less than 1. And I can multiply both sides by 5. And that means that x must be between negative 5 and 5. All right. Are there questions about any of this? I want to show you now visually what the hell we're doing, okay? So I have two ways I can do this. Let me do it this way. I started to do this at the beginning of class, but I ran out of time. My office mate showed up and she started talking to me and I got distracted. So let me see if I can do it this way. All right. So I have the code ready to go. I just have to edit it. Okay, so I'm going to put in the formula that we just came up with. It was, just bear with me for a second. It was negative 1 raised to the nth power, right? And then it was 1/5 raised to the n plus 1. I'm using k instead of n here. Hold on, I forgot my times. And then it was x to the, yeah, x to the k plus 4. That look right? That looks right. Okay, so now I'm going to take this, copy it. I got to put it here too. Oops. Okay, and the original function was x to the 4th over x plus 5. Okay, now I'm going to run this code the first time, so hopefully it'll come up. Okay, here we go. So this is what's in red here. Y'all get, if you have a question, you got it?
Yeah.
You sure?
Yeah.
Okay. All right, so this is the first time I've run this code, so I don't know how this is going to work. The red is the original function, which is the x to the 4th over x plus 5. Okay, we came up with a power series that we think will match up to this function between -5 and 5. Okay, let's see if it works. This is okay. So our original, we're starting out with 0. Let me start building this thing up. Oh, it went fast. Okay, so was our first term negative? It wasn't. Hold on. Oh, you know what? No, I forgot. The way I have my code, I have to do something here. Hold on. I have to make this -1. I have to change all of these. This is just for my code. Don't worry about what you're doing there. What you did is good. So 3, and then I got to copy this. Shit. Okay, let's see if that works. What was our first term? There we go. Okay, so there's our first term. So look at that. Hey, that's actually pretty damn good. Look, our first approximation there is pretty good, right? I would say that's pretty damn good. Let me zoom in. I only want to look between -5 and 5. Not bad for a first approximation, right? Now let me do another one there. Okay, so that's better, right? Didn't the dotted one was the one we had before. The black one is now the new one. Okay, it got closer over here. Over here, it kind of went away, didn't it? But it's all right. That's only the two terms. There's my third one. Look at that. See, it's gotten better. And if I keep doing this, I'm going to have to make this a little smaller. If I keep doing this, just look at it's just going to start converging to it, right? You see that? On the left side, I'm almost already on it. On the right, I'm doing some weird oscillating, but I'd say it's converged to it, hasn't it? So do y'all understand what we've done? We took an original function and we said, hey, we found a power series for it that works between -5 and 5. They match up. They're the same function between -5 and 5. And again, you might be sitting there going, well, we have the original function, so why do we need this? Just stand by, all right? Stand by. All right, let's look at another example. Let me back this off because the computer is probably doing something in the background. All right, there we go. All right, so we did, nope, we did those two, okay? Got it? Now, if you have a power series, right? If you have a power series, it would be nice if we could take this power series, because it is a function, right? We're saying a function, this power series now represents a function. Calculus 1 was about differentiation of functions, and Cal 2 has been about integration of functions. So it'd be nice if we could figure out a way to differentiate and integrate power series. And that's what this next note is about, the differentiation and integration of power series. And this is a theorem, which means that this has been proven to be true. And here it is. This is a big note right here. So this says that if you have a power series, now remember, this is the general form of a power series. Don't be thinking about that geometric series right now. The one that we're working with, just back burner that for now. Just think about a general power series. This is what a general power series looks like from last class. This is what we call the power series centered at A. This is what they look like. So this theorem says that this function, as long as you're looking on the interval of convergence, okay, it is differentiable, and this is what the derivative is. Okay, so I want to take this. I want us to come up with this on our own. It's not hard. Differentiating power series is not hard to understand. All right, so think about this. X is our variable. Let's differentiate. Okay, yeah, let's differentiate. This is what a power series looks like. So let's just start differentiating term by term, each one of these. Okay, let's just differentiate. So what's a derivative? If this is our function f of x, the derivative of this should be, well, what's the derivative of a constant? 0. Okay, so that's 0. Plus, I want you to look at this as a 1 power here on this thing. I want you to use chain rule. Okay, use the chain rule. So what would happen? 1 would come down, yes? So you get 1 times C1 times, now what's the derivative of what's in here? 1, right? Okay, plus, now do chain rule here. 2 comes down, right? 2C2, and then x minus a to what power? The 1 power, right? And then you have to take derivative of what's in here, which is 1 again. Okay, so we keep moving. Plus, now the 3 comes down, right? 3 in front of C3, x minus a to what power? 2, and then times derivative of what's inside, which is 1 again. This is just the chain rule and power rule, right? That's all this is. 4C4 x minus a to the third plus ... right? That's all it is. Now, if I rewrite this in sigma notation, watch. If I start my index off at 1, right? At 1, not 0, then I'm going to have what's the pattern here? Look at the coefficients. Each one, I'm ignoring the 0. I have 1, then 2, then 3, then 4. That just keeps on going up by 1, starting with 1. And then the subscripts on the C are 1, 2, 3, 4. Those keep going up by 1, starting with 1. And then look at the powers on the x minus a's. 1, 2, 3. But wait a minute, where are we starting it though? What's another way we could look at this 1? Could we look at it as an x minus a to the 0? We could, right? And then what we could say is that we have x minus a's in every one of these, but starting at what power? At 0, and then going up by 1. So I can write this like this. If we're starting at 1, it'll be n times c sub n, x minus a to what power? N minus 1, right? N minus 1. That's the formula for the derivative of a power series. If you start with this, here's what the derivative looks like. Okay? Now, look, check this out. I mean, isn't this just the power rule? Look at this. This up here, you have some number x minus a to the n. If I were to tell you to use the power rule on this from Cal 1, you would drop the power down, right? And then subtract 1 from that power. That's exactly what this formula is. It's exactly what that formula is. Now, there is one little thing we have to be careful with here. The index went up by 1. So we started here at 0, and when you do the derivative, the index goes up to 1. Technically, you could leave it as a 0. You could leave it as a 0 because if you plugged in 0, it would kill off the first term anyway. But I always put a 1 here. And a lot of books put a 1 here. Okay? It's just the power rule. Let's do an example. Let's do an example, then we'll talk about integration. So the example I want to do is to take this function that we studied last class, or maybe it was a class before. It might have been this class. That is the Bessel function. Remember me telling you about that? The vibration function on like a drum surface, a Bessel function. Let's take its derivative. All right. I think I asked you all to go, well, we did in class. I think we found the radius of convergence of this was everything, like negative infinity to infinity. So this is a valid function all the time. So we should be able to differentiate it. So if I differentiate this, all I need to do is make sure I've got the power series, which I do. And then I'm going to isolate all of this, everything here. That's basically the C sub n. And then the thing that's over here is our like x to the power. So according to the formula that we just came up with, this derivative should be the sum n equals 1 to infinity, all right? Because when I differentiate, my index goes from 0 to 1. And then what I do is I look at the power that I have on my x to the 2n, right? I drop it down in front. And then I take that x and I raise it to the 2n take away 1. That's just the power rule from Cal 1. But I also need the C sub n still here, like it still needs to be here. So I still need the negative 1 to the n, and then I need that all over the 2 to the 2n, and then n factorial squared. That is the derivative. Why did I not do the power rule on the negative 1 to the n and the 2 to the 2n? Why didn't I do any power rule or mess derivative with this? Why didn't I touch that? Yeah, this right here is our constant. It doesn't have x in it, right? We are only differentiating the thing that has x. So it's like in Cal 1, the constant comes for the ride. This time our constant is all of this stuff. So I'm only concerned about that. Now, let's just verify that this worked. Now, the way I'm going to verify it is this. I'm going to take this original function. I would like for us to write out the first few terms of the original function. So let's plug 0 in and see what we get. So we plug in 0. Will we be positive or negative? Positive, right? Plug 0 in here. X to the 0 is 1, right? X to the 0 is 1. So we're going to have 1 on top. And plug 0 into the bottom. 2 to the 0 is 1 times what's 0 factorial? 1. We define it that way. 1 squared is 1. So we get 1. That's our first term. Next term will be minus, won't it? We're going to start now. We're going to plug n equals 1 in here. So if 1 goes in here, what's my numerator? X squared. Good. Okay. And denominator? We're plugging in 1, right? So 2 to the 2 would be 4. And then n factorial. 1 factorial is 1 squared. So just 1. So that's it. That's that next term. Let's see if we can get maybe 2 more. Next term will be positive. Now we're plugging in 2, right, for n. So x to the 4th on top. All right, plugging in 2 for n. So 4 here, 2 to the 4th power is 2 to the 4th power, 16. And then times, okay, here, n factorial. So 2 factorial is 2, but then squared, so 4. Should we try one more? Okay, we'll try one more. Minus, it'll be x to the 6th, because now I'm plugging in n is 3, right? All right, and on the bottom, if I plug in 3, we get 2 times 3, 2 times 3 is 6, 2 to the 6th power, 64 times, okay, where are we at? 0, 1, 2, 3, we're at 3 factorial. So 3 factorial is 3 times 2 times 1 is 6, and then squared, 36, right? Plus dot, dot, dot. That's the original series, right? Written out, the first 4 terms of it. Now, differentiate it. Let's take the derivative of this, term by term. What's the derivative of this first one? 0, right? Because that's a constant. So here I'm doing j prime, j0 prime. So 0 here. And now for this is the same as like negative 1/4 x squared. I hope you're okay taking derivative of that. Bring the 2 out, right? So you're just going to get negative 1/2 x. What about on the next one? The 4 will come out, right? The 4 will come out and cancel with the 4, this 4 on the bottom. So shouldn't that be just 1/16 x cubed? And then on this last one, minus, it'll be x to the 5th on top. The 6 came out. Thank you, Cruz. So I'm canceling one of the 6s with the 36. That leaves me a 6. So 6 times 64, what is it? 384? Is that right? Yeah, 384. Okay, there we go. Plus dot, dot, dot. That's what the derivative should be. Is that what we get in our formula, right? This is what we came up with the formula for it. Are we going to get that? Is it going to create this? Let's see. Let's see. Let's go to our answer. Do y'all understand? All I'm doing right now is just verifying that the answer we got is right by checking it like mechanically. All right, let's plug in n equals 1 into this. So if n is 1, we get, let's see, 2 here. By the way, is it negative or positive? Well, I'll just put it here. It's 2, and then you have negative 1 because you're doing negative 1 to the 1. Plug in 1 here. What do we get? 2 minus 1, right? X. That on top, and then over the bottom, we're plugging in 1, so we get 4, and then times, let's see, 1 factorial squared is just 1. And that does reduce out to become negative 1/2 x. The first term matched. That's good news, right? That looks good. Let's do the next one. Okay, so now I'm going to plug in 2, right? I'm plugging in 2 for n. So I should get 4. That's 2 times 2. -1 squared would give us a positive 1. And then if I plug in 2 here, I get 4, should get x cubed. And then over to here, 2 to the 2 times 2 is 4, so 2 to the 4, right? 16. Oh, no, wait. Is that right? 16. And then we have 2 factorial, which is 2, then squared is 4. And the 4's cancel, and you get basically 1/16 x cubed. I'm not going to check the next one. Are you convinced, though? So what was easier? Is it easier to write out the terms of the series, differentiate each one, or is it easier for you to differentiate the power series using the power rule? I think the power rule, yeah. Writing it all out and then differentiating, that's kind of a pain, but that it can be done both ways. Yes, the C sub n is the constant, exactly. So you have to isolate it from the part that has the x in it, okay? All right. I hope that makes sense. That is differentiation. What about integration, though? What about integration? Well, let's do it. Let's try it, the general integration on this. If I asked you to find the antiderivative of this, right? Find the antiderivative of this with respect to x. Let's try it back here on this series part. With respect to x, let's find the antiderivative of this. So what's the antiderivative? Well, hold on. Anytime we take the antiderivative, we're going to have a constant, right? You always have that plus c? Always. Now, normally we put the plus c at the end, don't we? But see, this series goes forever, doesn't it? So I can't put it at the end. So anytime we do an antiderivative of a series, we put the plus c in the beginning. We just put a big constant there. Then we say plus. Okay, now let's start taking the antiderivative of each of these. So what's the antiderivative of c sub 0? What's the antiderivative of a constant with respect to x? Just that constant times x, right? So c sub 0 x. Yes? And then you take the antiderivative of this. So the way I suggest you think about this, if this is confusing, how would you take the antiderivative of this? If you look at it, let's just try and just do a specific example. What if I asked you to do the antiderivative of this? You could just pull the 4 out, right? So what I'm doing is I'm replacing that C1 with a constant, replacing A with a constant, so you can kind of see what it would look like. When you do this, the 4 could come out, you could ignore it, and then you do x minus 3 dx. Imagine that's to the first power. Could you do the power rule backwards, the reverse power rule on this? Would the antiderivative of this be 1/2 x minus 3 squared? And then you still have the 4 out front. Y'all see what I'm doing there? Is that the power rule backwards? Does it work? It does, right? I'm just taking this, I'm adding to this power, so it becomes, I add 1, I get 2, and I have to scale it by 1/2. That way it kills the 2 off when it comes out, right? On the differentiation. So what would that mean this one becomes? What is it? What does this one right here become? 1/2 C1 x minus a squared. And each of these would work the same way, wouldn't they? Each of these would work the same way. This would become plus 1/3 c sub 2 x minus a to the 3rd. And then this one would be 1/4 c sub 3 x minus a to the 4th. 4th plus dot, dot, dot. Y'all with me? Now this next part is a little confusing. Let's see if you can follow this. I would really like it if this was really C sub 0 x minus a to the first power, right? Wouldn't that be nice? Because if this first piece was C sub 0 x minus a to the first, then the next one would be 1/2 C sub 1 x minus a to the second, and they would all follow the same pattern, wouldn't they? It is though. C sub 0 x is this. Why? Or I guess I should say it's not, I'm not
Constant.
saying it is that, it can be that though. We can represent it this way. Why though? Let me see if I can make this make sense. What would happen if I distribute this through? What would I get? C sub 0 x, oops, C sub 0 x minus what? A times C sub 0. But what is A times C sub 0? No, it's some constant, right? And aren't we already adding a constant out here that we don't know? So why don't we just take whatever we need from this constant and just subtract it here? All right, so what I'm saying is take this in yellow, steal from this constant negative a C sub 0 from it, and slap it in right there, and then you can factor out the C sub 0 and you would have it. So because we have that plus C, and that C can be any constant, we can always take anything away from it, subtract 1, add 1, doesn't matter. You'll still have a plus C on the outside. So it's tricky, but we're not breaking any rules here. This really is some constant plus C sub 0 times x minus a, and then the rest of this. Which means I can rewrite it in sigma notation like this: C plus sum n equals 0 to infinity of C sub n x minus a, sorry, I'm missing one thing, to the n plus 1 all over n plus 1. So what I'm doing is I'm basically doing the power rule, right, for integration. Remember the power rule for integration? You add 1 to the power, but you have to divide through by that. Same exact thing. Check that this formula works. If you plug in 0, you get C sub 0, and then this becomes x minus a over 1, which is this first piece. And then if you let n be 1, you'll get this. N be 2, you'll get this, and so on and so forth. So the big end of story here is that to do antiderivatives of power series, you're just going to do the power rule. That's all you're the power rule for integration, and you're in business. All right. Let's do an example. I'm going to actually do the last example because we just talked about this. I was going to do it at the end, but I would like for us to see if we can do this one. I want us to find the antiderivative of 1 over 1 plus x to the 7th using a power series. Now, if I asked you to find the antiderivative of that right now without power series, you wouldn't have any method to do this. You wouldn't be able to do it. In fact, let's go to Wolfram alpha. Let's go to Wolfram alpha, maybe. Where to go? Up here. What the heck is that? Okay, let's integrate 1 over 1 plus x raised to the 7th. And let's just see what it does. I'm going to guess it's not going to be able to do it in a closed form. It's thinking. Oh, it was able to do it in a closed form. But that looks pretty nasty. That looks pretty nasty. Yeah. I don't think we're getting that by hand. And I sure as hell don't want to try. I don't want to try. So let's see if we can do it with PowerSeries instead. Okay. Now, what's amazing about technology these days is if you scroll down, right, I've shown you this already, it should give us the series of this, but, well, you know what we could do? We could do this. We could say, let me see if I just type in integrate series. So will it be smart enough to integrate the series for this? While it's thinking, let's get to work. Okay, so first thing I'm going to do here is this. I'm going to look at the 1 over 1 plus x to the 7th. And I need to integrate that, right? So can we come up with a series for it? How? Doesn't that look like the geometric from earlier, right? Doesn't that look like what we were doing a little while ago? We could rewrite this as 1 over 1 minus negative x to the 7th, right? Couldn't we do that? And then that I know is sum n equals 0 to infinity of negative x to the 7th to the n, so long as the absolute value of this is less than 1. If this is true, right? Got it? Let's write out the first few terms. If n is 0, what do we have? If n is 0, 1, right? Because this gets raised to 0, it's 1, right? Okay, and then the next term, let's see, if we plug in 1, we should get a minus here, shouldn't we? Minus x to the 7th. Plug in 2, what do you get? Positive, right? X to the 14th minus x to the 21 plus x to the 28. And I keep going, right? I'm going to stop eventually here. X to the 35 plus dot, 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 right? That is the series for that. Got it? Now, integrate it. Integrate it. I'm not even going to use the power rule formula. I'm just going to integrate that. Okay, just integrate it. Let's see what we get. What's the antiderivative of, well, we have a constant, right? We don't know what it is. Okay, plus antiderivative of 1. X. Antiderivative of negative x to the 7. Negative 1/8 x to the 8th. Okay. Next one, plus 1/15 x to the 15th minus 1/22 x to the 22nd plus 1/29 x to 20. Isn't this easy? Like, you understand what I mean? Like, isn't the integration like really easy? Plus dot, dot, dot. That's the antiderivative. That's the antiderivative of that function. And if you're not happy with how accurate it is, I just go more terms, and as many terms as I need to make you happy, I'll do it. Let's go back to Wolfram Alpha, see what it did with that. Still thinking. Okay, so let's do this. Let me take out integrate, and let me just ask it for the series of this. Okay, so it gave me, oh, here we go. This is the series expansion. Okay, so right now, don't worry about this. This is a Taylor series. We haven't talked about, well, this Taylor series about 0. This is a Lorentz series. Don't worry about that. Let's just do this one right here. This is what we had, right? 1 minus x to the 7th plus x to the 4th. So if we take this one, let's do more terms. It's probably going to want me to get the pro version or something now. Oh no, it's giving me some more. There we go. So here's more terms, right? So I'm wondering if I can take this. I can't copy that, can I? But I mean, once you're here, you can integrate it, right? I mean, that's easy to integrate. Okay. All right. Back to the notes. All right. So we are going to look at example. We did this one. All right. Things are about to get tricky. All right. So when you look at this initially, maybe you see this. Maybe you see this. Maybe you see that this is really 1 over 1 minus x, all of it squared. Isn't that the same thing? That's the same thing, right? And the 1 over 1 minus x, isn't that the geometric series thing we've been talking about? Like we have a way to turn that into a series. So this would be equal to sum n equals 0 to infinity of x to the n squared if the absolute value of x is less than 1. That's true, right? That is not a power series representation. We have not converted that into a power series. What we've done is we've converted into the product of two power series, right? That's what this really means. Take that power series and multiply it times itself. And that is not a power series. The product of two power series is not a power series has to have one summation in it. It can't have multiple summations being multiplied. And the reason why is, think about this. This is an infinite list of things, right? This first one is a bunch of things being added together forever. And then you want to multiply that times another list of things that are being added together, right? Like that. And when you do that, even when you try and do like the first multiplication, right? This first one through, you got to go forever, right? And then you go to the next one. So this would not, this right here, this answer would not qualify as a correct power series representation of this function. Because again, it's the product of two power series. So we got to do something different. All right. So this is not going to work because you have product of two power series. We want to get it to one power series. So you can look at this for like the next year and maybe not see it until someone shows it to you. All right. So I'm going to show you this. I want you to notice this. Notice that if we take the thing that we do know the power series of, this is the one that we know is geometric, right? We can convert this to a power series, right? Notice that if we take that and we take its derivative, what we get. Take the derivative of that. So if you don't like the way that's written, rewrite it this way. 1 minus x to the negative 1. Bring it to the top and then take the derivative. What do you get when you take derivative of this? So chain rule, right? Bring your negative 1 out. 1 minus x to what power? Negative 2. And then don't forget the chain rule, right? Negative 1 came out. This to the negative 2, then the derivative of the inside, which is negative 1 again, right? So times negative 1. And when you clean all that up, what do you get? Oh, 1 minus x to the negative 2, right? But isn't that just 1 over 1 minus x, that quantity squared? And isn't that the thing I'm asking you to find the power series of? Yes? Right? I'm asking you for the power series of this. But we've recognized that this is the derivative of this, right? In other words, we can write it this way. So 1 over 1 minus x quantity squared is equal to the derivative with respect to x of 1 over 1 minus x, isn't it? That's true. That's what we just showed. But this is the same then as the derivative with respect to x of the power series for that, right? If the absolute value of x is less than 1, this is true, right? So saying that this is equal to the derivative of that is same as saying that this is equal to the derivative of this power series as long as the absolute value of x is less than 1. And do you know how to take derivative with respect to x of this power series? Yeah, power rule, right? Here's what's c sub n for us here. What's the constant? 1, it's always 1. So this is your good old just do the power rule. So the derivative of this would be sum n equals, now we took the derivative, right? So the index will go up to 1, infinity, n times x to the n minus 1. So I just applied the power rule to that series. So I no longer have the differentiation. And that is the answer. That is the power series for that function. Now let's write out a few of the terms. If n is 1, we should get 1, and then we should have plus. If n is 2, we should get 2x, then plus 3x squared, then plus 4x cubed, plus 5x to the 4th, plus dot, dot, dot. Okay? Questions? Do y'all want to see if it's right, or do y'all trust it? I don't care. I'll do one more. Okay, so our answer was what was it? It was n, so I need to do k minus 1, and then it was x to the, well, it was what? It was n minus 1, so I'm going to have to go x to the k minus 2. All I'm doing now is checking to see if it's going to match up to that function or not. And the function was 1 over 1 minus x squared. All right, let's see if we got this right. So there's the function 1 over 1 minus x squared. Here it is. And here's my approximation. 1, 2x. Do y'all see the black? The black is not a very good approximation of the red. But what should happen is that as long as we're looking between, we need we need this to be -1. As long as we're looking between -1 and +1, go somewhere around here. As long as we're looking in this little window between -1 and +1, it should start to converge. It is, right? You see it starting to become that function? And I know that, again, y'all are still like, well, who cares if it's just that little window? Next chapter or next section, we come up with what's called the Taylor series, which allows us to move left and right. We can move it. So if we want it to match in a different region, we'll just move it over. All right. That's what's happening visually. And isn't that our series? That was the series, wasn't it? 1 plus 2x. All right. Back to the notes, back to the notes, back to the notes. All right, that was this example. Now let's look at this one. I'm going to let you think about this one for a minute. Can you express that as a power series somehow? Take a moment. Feel free to talk to each other and give you 5 minutes to see if you can come up with anything on this. All right. Somehow, from what we've talked about today, that can be rewritten as a power series. It's related to the last problem in the sense that there is a connection between this and that good old-fashioned geometric series that we started today with. You've got to figure out what that connection is, though. You got anything or no?
So we think it's similar to this integrated.
Integrated, so you think that that's the integrated form of the geometric series that we've been looking at? Okay, let's see if we can find that connection. You're saying that if we take the original, do you want me to take the original one? Like this and find the antiderivative? Yeah. The antiderivative of that would be definitely a natural log, right? Because it's a constant over linear. So it'd be natural log of the 1 minus x, but you would also have, you would have a plus a constant, but wouldn't you also have a -1 on the outside? Because when you take derivative of this, it would create derivative natural log of this would be 1 over this, right? But then you have to take derivative of what's inside, which is -1. You don't want that -1 there. So you have to scale it out. I agree with this, but we have a plus here, right? And that's not a plus.
Wow,
No.
double negative?
Double negative. So make it a minus minus.
Yeah, to match up with the U to the N geometric series.
Okay, so, well, let's do this. Yeah. What if we do 1 plus, let's just look at this one right here. Look, what would the antiderivative of that be? That would be this, right? And that's exactly what we want, right? You don't have to worry about scaling. Yeah. So the thing we're actually looking for, right? We're trying to find the power series for this. The thing we're actually looking for is just the antiderivative of this, right? the integral of this. So let me scratch this out. But the 1 over 1 plus x can be rewritten with a double negative, 1 minus minus x. So I can write, so I'm working with this. I'm going to work the left side, I mean the right side down. This is equal to the antiderivative of 1 over 1 minus negative x dx, right? But what I just put there can be rewritten in a series. This can be rewritten as the series n equals 0 to infinity of negative x to the n dx. That's what our natural log of 1 plus x is, right? Now, I'm going to get rid of the c on the right-hand side because I'm going to get a c when I do this. Okay, this is going to give me a plus c. Y'all understand what I did there? Just rewrote this as this and then rewrote this with its power series. Now, I want to integrate this, but I have to make it look right. I have to separate the negative from the x. So I'm going to go integral of sum n equals 0 to infinity of negative 1 to the n x to the n dx. And now I can integrate because I have the x to the n by itself. And then this part right here, negative 1 to the n, that's that c sub n. That's our constant term that won't get changed with the integration. So this should be equal to natural log of 1 plus x. And so now let's go ahead and do the antiderivative. The antiderivative of this would be sum n equals 0. So when you do the antiderivative, the n still stays at 0. When you do the differentiation is when it changes to 1. So we're integrating, we're going to keep it there. And then I'm going to write it like this, negative 1 to the n, x to the n plus 1, because I'm using power rule, but for integration over n plus 1. Plus some constant must equal natural log of 1 plus x. Understand? Now I'm going to do one more thing. I'm going to rewrite this as c plus, let's write out the first few terms of this. So if n is 0, we get a positive number, we get x on top, and we get a 1 on the bottom. So this should just be x. Next term will be negative. So now I'm plugging in 1 for n, and I should get x squared over 2. So 1/2 x squared. Then plus, now I plug in 2 for n. So I get x to the third and then 1/3 x to the third plus, no, minus this time. Are y'all okay with what I'm doing? Just plugging in n, different values of n? Plus dot, dot, dot. This is equal to natural log of 1 plus x. All right. One more thing and we're going to be done. One more thing. I mean, this is basically it, right? The problem is this plus c. Does anyone have questions? Sure. Okay. One more thing I can do. I have a constant here. I don't know what it is, but we know something about this natural log function, don't we? We know that the natural log of 1 is 0, don't we? So I can use that to figure out what c is. So to find c, let x be 0 on both sides of this equation. If you let x be 0, then what does this equation become? C, right? C, and then everything else goes away, right? Because all these have powers of x the whole way down forever, equals the natural log of 1, which means that c is 0. Understand how I got c? Looked at this equation and said, wait a minute, I know the natural log of 1 is 0. So if I let this x be 0, it kills off everything here and just leaves me with c must equal natural log of 1, which is 0, which means that c equals 0. Our constant is 0, which leads us to our final conclusion, which is that natural log of 1 plus x, has a power series of x minus 1/2 x squared plus 1/3 x cubed minus 1/4 x to the 4th plus dot, dot, dot. That's your power series. All right, somebody break out their calculator. Okay, I want you to break out your calculator real quick. If you have it. And I want you to type into your calculator natural log of 1.5 and tell me what you get. Is approximately 0.4 what? 0.05. Now, what did your calculator just do? Does it have any idea what the natural log function is? No. What it did was it took what number? So look at this formula right here, 1 plus x. What would x be if we plugged in 1.5? What's x for us then? 0.5. Now take 0.5 and plug it into this. So now in your calculators, I want you to do 0.5 minus 1/2 times 0.5 squared plus 1/3 times 0.5 to the 3rd, and then minus 1/4 and then 0.5 to the 4th. I know that's a lot to type in, but somebody try that and tell me what you get. I bet it's going to be close to 0.405. We'll see what people get. Maybe it's not close to 0.405. Maybe we need a lot of terms to get it. Did you get something or no?
It's 401.
It's 401? You got 0.401? Okay, so maybe we need some more terms. What would the next one be? Plus 1/5, 0.5 to the 5th, right? And the more you add, the closer, I promise you're going to get to 0.405. Your calculator has within it, within the memory in this calculator, every single one of these keys when you type it, cosine, sine, tangent, natural log, e, all of them have a predefined power series that's programmed into the memory. And so when you type in something like this into your calculator, that's what it's doing. It's doing this. It's not doing any natural log or sine, you know, it's not doing a unit circle or anything. It's not doing, it's just doing a power series. And then if you want, you know, when you can ask your calculator for more decimals, right? It just goes further out into the series. I told you all that at the beginning of all this. That's the way the calculator works. But now you can actually see where it's coming from. All right, let's get back to notes. What's going on to 15 minutes? Okay. One more example. Is there any way we can express this as a power series using that geometric thing that we've been working with? So anyone have some sort of connection here between this and that 1/1 minus x?
Yeah.
1 plus, wait, integrate. Okay, you're saying that thing integrated. I heard something online. Ian, do you have something?
Yeah, I said the same thing.
Okay.
Isn't it derivative 1/1 plus x squared?
Yeah,
The
yeah.
derivative of arctangent is 1/1 plus x squared, right? Let's look at this. The derivative with respect to x of tangent inverse of x is equal to 1/1 plus x squared, right? That's what the derivative of that is. which if we want to find the power series for this, right? Then all we need to do is find this power series, right? And do what with it? Integrate it, right? So saying that the derivative of this is equal to this is the same as saying that the tangent inverse function is equal to the antiderivative of 1 over 1 plus x squared dx. To say the derivative of arctangent is this is the same as saying that arctangent is the antiderivative of that. Yeah? This we should know from just our stuff we did earlier this semester. The antiderivative of 1 over 1 plus x squared should be our inverse tangent of x plus a constant, right? Plus a constant. So what I'm going to do now is basically, this is the same as the previous problem, isn't it? All I'm going to do here is rewrite this as 1 over 1 minus negative x squared, right? And then rewrite that as its series. Negative x squared to the n. And then I'm going to rewrite that as negative 1 to the n x to the 2n dx. Which now at this point I've separated the c sub n from the x to the power. So I should just be able to use power rule. So now when I actually take the antiderivative, I get sum n equals 0 to infinity, negative 1 to the n, x to what power? 2n plus 1 over the whole thing over 2n plus 1. So I add 1 to the power and I divide through by it. And then I have to add a constant to that, right? Let's write out the first few terms of this. And I'm going to put the constant out front. So if n is 0, we'll get what's that?
Where did you get the denominator?
I'm using the power rule on this. So, remember when we're doing antiderivatives, right? Antiderivative, the power rule says you add 1 to the power, but you have to divide through by it,
Oh, right.
right? So I'm adding 1 to this power, and then I'm dividing through by that.
Oh,
Yeah.
okay.
All right, so when we plug in n is 0, what do we get? Just x. And then the next term will be a negative. So then we'll get, we're plugging in 1 for n, so I believe we get x cubed, and on the bottom 3, so 1/3 x cubed. And then we should have plus on the next one, and I think we're getting odd numbers here, aren't we? And they're alternating, so 1/5 x to the 5th minus 1/7 x to the 7th plus ... right, forever. And this is what arctangent of x is. Is there any way we can figure out what c is? Plug 0 in, because we know what inverse tangent of x is, right? We know what inverse tangent of 0 is. It's like, at what angle do you get tangent to spit out 0? At 0, right? So we know if we plug in 0 for x, we should be able to solve for c. So if we let x be 0, we get the left side of this equation becomes 0, and the right side of the equation becomes c. So c is 0 again, which gives us a final version of our answer, which is that the inverse tangent of x is equal to x minus 1/3 x cubed plus 1/5 x to the 5th minus 1/7 x to the 7th plus ... We have the power series for arctangent. This one is actually pretty, this one would be, I think this one would be fun to look at. Because if we graph arctan x, okay, the series we just had, it was -1 raised to the n, right? And then it was x raised to the 2n plus 1, but I have to put a negative. I do n minus 1, 2n minus 2 plus 1, 2n minus 1, yeah. 2n minus 1, so 2k minus 1. Okay, that should be it. I'm thinking out loud, just ignore that for now. There's the arctangent. Oh, this is going to be awesome. Watch. There's the arctangent function, right? And the arctangent function goes in both directions forever. Let's see. Yeah, we should have it. Let's see what happens. Okay, right now the black line is our approximation. It sucks. That line's better. X minus x to the third. Wait a minute. Something's. Oh, I forgot to divide. Hold on. I forgot to divide this whole thing. Divided by 2k minus 1. Okay, I forgot to do that. I need that. Copy. Sorry. Like I said, I was trying to get this done before class, but I just didn't have time. Okay, let's try that again. Okay, our line, not very good. Better. Well, better in here, right? Better. It still has a convergence radius. We still have between, I believe, -1 and 1. Oops, yeah. So in that little window, I mean, we're like really matching up to this really good. Oh, you can see it here. Watch what it does on this edge. See how it starts to, it's like coming out very slowly towards that. Let me do a bunch of them. See if I can't bring my computer to its knees. Yeah, I think it might still be thinking. Yeah, it's still thinking. Okay, there we go. All right. All right, that's it for this section. All right, yes.
I'm trying to understand how x equals 0 made the C go away.
So if I just replace x with 0 on both sides, are you okay with all of this goes away? All of that goes away, right? If I replace x with 0, all I'll have is c.
Yes.
Then if I plug 0 into this, you need to know what arctangent of 0 is.
Okay.
So it's basically saying at what angle do you plug into the tangent function where it'll spit out 0? So if you plug 0 into tangent, it spits out 0.
Right.
So if you take the tangent function, right? Tangent, and you plug 0 in, tangent of 0 is 0. So if you go backwards, the inverse tangent takes 0 back to 0. So if I plug 0 into this, arctangent of 0 is 0, which means the left side is 0.
Thank you.
Mm-hmm. All right, so that's it. Look, the homework problems, some of these are a little bit weird. There's one in particular that is a little bit strange, well, a lot strange. We'll see how you do with it. I want to give you just a real quick preview of something I'm going to do next class. This is pretty exciting, I think. Have y'all ever seen what is argued to be the most beautiful equation in math before? Y'all ever heard of this before or seen this before? E to the I pi plus 1 equals 0. Have y'all ever seen that before? Ever heard of this before? No? So mathematicians will debate this. A lot of mathematicians think that this is the most beautiful equation in math because that is a true statement, okay? That is a true equation. And the reason why people like it and think it's so beautiful is because it contains all the most important numbers that we use in math, all wrapped into a nice little package. And some of the numbers you may look at initially and be like, oh, well, that's not a very important number. But let's just take, for example, the number 0. The number 0 is actually really important in our mathematical system. This is called the additive identity. And our number system makes up what's called a field. A field is, well, okay, I won't get too much into. There are these things called the field axioms. If you have a set of numbers and you have what are called 2 binary operations, addition and multiplication, then if the set of numbers has a certain structure to it, it is called a field. It's a very, very strong condition to be a field. A lot of things have to work out properly. And one of the things that you have to have is you have to have an additive identity, which means that you have to have something in the set of numbers that when you add it to the other numbers, nothing changes. 0 is the additive identity. 1 is what we call the multiplicative identity. Our number system, again, to be a field, you must have a multiplicative identity within the field. It's some number that when you multiply it times all other numbers, it leaves it unchanged. So 0 is the identity that you add 0 to anything, it doesn't change it. 1 is the number that when you multiply times anything in the number system, it doesn't change anything. So that takes care of 2. These are really important numbers. And then, of course, we've seen E and pi, right, are super important. I mean, pi obviously has something to do with the circumference of a circle divided by its diameter. That's what pi is. Then E, we've seen that E is this really, really special thing from Cal 1. The exponential function just grows a certain way that it is its own derivative. It's really strange. I'm just going to say this is important, okay? And then the one that really is surprisingly here is I. That's the one that's like, whoa, what's this doing here? Because I is the square root of a negative number, the square root of -1. And that you've learned that this is called the imaginary unit. That brings in the imaginary numbers. And your whole life you've been told like these are imaginary numbers and you haven't really done much with those ever, right? We've stayed away from these intentionally. So this equation brings all of these important numbers in math together into one nice package. In next class, I will show you why it's true. I will prove to you this is true. And the way I'm going to do it is with PowerSeries, right? And I'll be able to hopefully prove to you that this is true. Okay? All right. Y'all have a good one. I'll either see you here in class or not. On Wednesday, I will be here. Y'all have a good day. Thank y'all for showing up. I know it was rough the last few weeks or last week or so. Everybody at home okay?